Hello students, now today we are going to discuss adder. It is a combinational logic circuit. So generally what happens in adder, in binary adder, suppose if I will tell you 7 plus 5, so 7 plus 5 it is nothing but is what? 12. So basically what happens in our childhood, from beginning we have started for as addition. If we add 2 bits, 7 plus 5, the result, the sum is nothing but is your 12. It is your sum is your 12. So I will say that, so that the first bit it is represent the sum, and here we can say that is your carry. This is your carry. Okay. When you will add 2 bits, so one in result you will find the sum, one bit is your sum, another bit is your carry. So anything if you will add 2 numbers, suppose 47 plus 25, so 7 plus 5 12, then carry 1, here 4 plus 2 6 plus 1 7, here 72, and we can say that this is your sum. Suppose if the sum, this is your 2 bits and this is your 2 bits, this is your what? This is your 47, add with 25. Suppose if I will say that is your 49 plus 72, what happens here? 9 plus 2 11, then carry, this is your 12, and here this is your 2 bit, this is your 2 bit, and we can say that this is your sum, and here this is your carry, this is your carry. So what happens in your adder? If you add 2 bits, so one bit is your sum, in result that is your one, that is your sum, another one is your carry. Similarly, in case of binary adder, when you will add 2 binary bits, that is your, in result you will find sum, another one is your carry. In case of adder, first of all, if you add 2 bits, 7 plus 5, that is your 12 here. Suppose if I will say that is your 3 plus 5, that is your what? The sum is your 6. That means if we add this bit with this bit, the result, the sum is your 6 bit. In this sum, there will be no carry here. There will be no carry. So in case of adder, there are the 2 things. One is your half adder, another one is your full adder. In case of adder, so it categorically we can say that one is your half adder, and is your full adder. What is half adder and what is full adder? In case of half adder, if the sum, the result, it will not produce carry, then the half adder only add 2 significant bits and the result is your sum. And if there will be a carry, then the half adder does not, that means the half adder will add only 2 significant bits, that is your what? You will find only without carry. But in case of full adder, so that is your what? If you here, if you look at this one, 9 plus 2 11, that is your 1, that is your carry 1. In second bit, that means 4 plus 7 plus 1, that is your carry. In this second bit, that is your MSB, it is add 3 bits. So I can say that, suppose this is your A0, this is your A1, this is your B0, and this is your B1. So here A0 is 9, B0 is your 2, and here A1 is your 4, B1 is your 7. And if A0 plus B0, that value, this is sum is 1, and if there is a previous carry, this carry represents what? In this one, that means the half adder will not take into account the previous carry. So in that case, the full adder not only add the 2 significant bits, but also consider the previous carry. So that's why in full adder it is a combination logic circuit. It will add 2 significant bits, A with B, A plus B, along with the previous carry. That in this case, the half adder does not add these 3 bits. The half adder only add 2 significant bits, and the result will only sum. So that's why in case of half adder and full adder, so half adder, so this is your, in case of half adder, there is a 2 bit, it will add 2 significant bits. Suppose I will say A and B, and the result, that is your one is your sum, and another one is your carry. In case of adder, so if we draw the truth table, truth table, this is your AB, this is your input, and in output there is your what? One is your sum, another one is your carry. So in case of digital logic circuit, so if the input is 2, there are 4 combinations. So that is your 0 0, that is your 0 1, and 1 0, and this is your 1 1. If we add 2 bits A with B, 0 plus 0 0, that's why the sum is 0 and carry is 0 here. Here 0 plus 1 1, 0 plus 1 1, that is your sum 1 and carry 0. Here 1 plus 0, 1 plus 0, the sum is 1 and carry is 0. And 1 1, if I will add 1 plus 1, that is your what? The carry will be 1 and the sum will be 0. That is what? This is the logic truth table of the half adder. So here, in case of sum and carry, this is your input. In half adder, this is your, we can say, this is your inputs and this is your output. In output, one is your sum, another one is your carry. In case of adder, if input is your 2, if you add A plus B, A with B, the sum is what? A plus B and carry. And the carry is nothing but what? Here, when A1, B1, then only the carry will be generated. Otherwise, the carry will not generated. If you look into these 4 cases, 0, 0, 0, 1, 1, 0, 1, 1, the sum will be generated when either A0, B1 or A1, B0. But in case of when A1, B1, then the sum will be 0 and the carry will be 1. So what do you observe in this truth table? This truth table indicates that the carry will be generated whenever both A and B are 1. So that's why in case of half adder, how to develop the logic circuit. When you are going to design the logic circuit, that's what? Whenever the output is 1 here. When the output is high, there are 2 outputs. In case of half adder, we have the 2 input and 2 output. In 2 output, one is sum, another one is your carry. In case of sum, first of all, when you are going to design a logic circuit, design the digital logic circuit, design the logic circuit, first of all, in output, we have to notice when the output is high or when the output is 1, or that is for sum, the output is 1 here and here, and notate the corresponding input. If the sum is 1, the corresponding input is what? A0, B1. When here the sum is 1, the A1, B0. Then we have to write the equation for output, that is a sum. For sum, first of all, write down the logic equation or Boolean equation. First of all, when we are going to design the logic circuit, first procedure is what? Develop the logic. And second one is what? Prepare the truth table or logic table. Number 3, derive the logic equation or Boolean equation. This is the logic equation for a Boolean equation for output. Finally, minimize the logic equation or Boolean equation. Then final stage, design the logic circuit. In case of half adder, the 2 input and 2 output, we have to write the logic equation or Boolean equation for the output. For sum is this is 1 and this is 1, and notate the corresponding input here. For this one, there is your 0 for false, 1 for a true, 0 for A bar, 1 for B, true value. That's why the mean terms you have to notate, you have to count. Here S equal how much? That is your A bar B plus A B bar. A B bar here. Here for 1, that is your A and B bar, 0 for complement. So that's why A B bar. So S equal to A bar B plus A B bar. If you have to minimize this, A bar B plus A B bar is nothing but A XOR B. Sum S equal to A XOR B. Okay. So this is the logic equation or Boolean equation for output of the half adder sum. Then carry. So then derive the logic equation or Boolean equation for carry. So tell me. So that is your what? For carry, C equal to how much? C. When the output is 1 here, the carry is generated when both A and B are 1. So this is 1, 1. So that is only one mean terms, that is your C equal to AB. The C equal to AB. That is your carry. So we found the for output equation For half adder, one is sum, that is your A XOR B, and carry equal to AB. So that's why, so in a case of half adder, this is your half adder. If the input is AB, output is what? One is sum, the value is how much? That is your A XOR B, and carry is what? This into this, that is your AB. So one thing is, the carry will be generated when both the inputs are logic level high, that is your 1 1. Our sum is generated either A0, either B1 or A1. So we found, as far as conclusion, in case of half adder, the sum will be generated either A or B1, and carry is generated both A and B are logic level 1. This is in case of the design of the logic circuit. So in half adder, one is sum, another is your carry. The sum value is how much? A XOR B, and carry value is nothing but A into B. So in case of using gates, so design the half adder using gates. Gate means what? And or not, NAND nor, or exclusively for NAND gate, exclusively for NOR gate. So, or exclusively using basic gates. Basic gates means and or not gate. In case of AB, this is your A and this is your B XOR gate. This is what? That is your sum equal to A XOR B, and carry is nothing but what? That is your what? AB AND gate, that is your C equal to AB. In case of half adder, that is your half adder consists of one XOR gate and one AND gate. So one is sum, so another one is your carry. Okay, in case of half adder, so it has two input A and B, it has two output, one is sum, another one is your carry. So sum is nothing but A XOR B, or that is your A bar B plus AB bar, and carry is nothing but AB, that is your both A and B are logic level 1. Then come to, that is your full adder. Full adder. So full adder, it is a combinational logic circuit. Full adder, it is a combinational logic circuit. It consists of two inputs A and B along with the previous carry. The previous carry is nothing but your CI. So I already told you, when I will add, suppose 49 plus 75, that is your what? 9 plus 5, 14. Then carry 1 here, that is your what? 12. So this bit, in this stage, in first stage, that is your 9 plus 5, that is your 14, that is your sum, and carry 1. In this stage, half adder add only two significant bits, that is your A with B. But in case of this bit, this stage, not only add 4 plus 7, you have to consider the previous carry generated by the what? The first LSB 9 with 5. So 9 plus 5, this is generator carry, that is 1 here. In this stage, you not only you consider 4 and 7, but you have to consider, that is your what? The previous carry. So okay. So in this case, that is your what? This is your A, this is your B, and this is nothing but your CI here, full adder. Full adder, consider the two significant bit A and B along with the previous carry CI. Similarly also, in output also one is your sum, another one is your what? That is your carry. So we have to prepare the truth table. How to prepare the truth table to design the combination logic circuit full adder. In case of full adder, notice there are 3 inputs. If there are 3 inputs, how many number of combinations? There are 8 combinations. So input is your what? That is your A, that is your, first of all prepare the truth table, A, B and CI. If there are 3 inputs, there are 8 combinations from 000 to 001, 010, the decimal value is 00113, the decimal value of 100, that is 4, and here also 5, this is your 6, and this is your 7. There are 8 combinations. If there are 8 combinations, you may consider the decimal value here. The decimal value 0, 1, this is your 2, 3, 4, 5, 6, and 7. If there are 3 input, maximum decimal value will be 2 to the power 3 minus 1, 2 to the power 3, that is your 8, 8 minus 1, 7. So maximum decimal value 1, 1, 1, that is your 7 here. So output, this is your inputs. And output is nothing but what? Outputs. Similarly, one is your sum, that is your S, another one is your carry, that is your C. Look at this here, A plus B plus Ci here, 0 plus 0, 0 plus 0, Ci, previous carry was 0. So 0 plus 0, 0, that is your sum 0, carry 0. Here 0 plus 0, 0 plus 1, that is sum 1, carry 0. Similarly 0 plus 1, 1, 1 plus 0, 1, the sum 1, carry 0. Here 0 plus 1, 1, 1 plus 1, 1 plus 1, that is your 1, 0. The 1 plus 1, if you add 1 plus 1, that is your 0, that is your carry here, carry. If you add 1 plus 1, the sum will be 0 and carry will be 1. 1 plus 1, the sum will be 1, 0, the carry will be 1 here. Similarly, 1 plus 0, 1, 1 plus 0, 1, the sum 1, carry 0 here. Here 1 plus 0, 1, 1 plus 1, that is your sum 0 and carry 1. Here 1 plus 1, 1, 0, 1, 0 plus 0, that is your 1, 0. That is your what? Sum is 1, 0 and carry will be 1. Similarly, 1 plus 1, 1 plus 1, 1, 0, 1, 0 plus 1, that is your 1, 1. If you add 1, 0, 1 plus 1 plus 1, that will be 1, 1. So that's why the sum will be 1 and carry will be 1. So this is all about your truth table of full adder. So then what we will do? First is prepare the truth table. Second step, derive the logic equation or Boolean equation for the output for sum and carry. Okay, for sum, we will found the sum S. Tell me what is sum? When the output will be high here, in this case, the output will be high here. For S equal 1, tell me the 0, 0, 1, the decimal value will be 1. So that is your 1. For here also 0, 1, 0, 0, 1, 0, the decimal value will be 2. Similarly 0, 1, 1, that is your 3. And here, that is your what? So no, this is your 1, 2, 1, 2, this is your 4. This is your 4. And this is your here 1, 1, 1, 1, that is your 7. So you may calculate here, that is your 1, 2, 4, 8. If you check 1, 0, 0, 1, 0, 0, this is 1, 0, 0. The decimal will be how much? This 1 means what? This is 4. The value will be 4. If you will say 1, 0, 1, this will be 4 and this will be 1. 4 plus 1 and this is nothing but is your 5. So here, so earlier classes of digital electronics already I discussed. So how to the equivalent binary of corresponding decimal numbers. So that is your for sum derive the find out the mean terms. We can say these are the mean terms is represented by that is your sigma. The mean terms are where that is your 1, 2, 4 and 7. If you write it like this here, 1, the corresponding mean terms are what? A bar, B bar, Ci. This is your A bar, B bar and this is your Ci. Plus summation means addition. Then second one 0, 1, 0, that is your A bar, B, Ci bar. A bar, B, Ci bar. Then this one A, B bar, Ci bar. A, B bar, Ci bar. Then plus here A, B, Ci. A, B, Ci. Okay. So this is your logic equation for the output sum. You can easily calculate it with the help of KMF techniques. You can find the minimize this value. If we consider this one, we require more number of hardwares to design the full adders. To minimize the minimum hardwares, so you have to minimize the logic equation or Boolean equation. Once we minimize the logic equation, the number of gates should be reduced. So you can use using Boolean theorem or Boolean postulates, you can solve this logic equation also. So okay, so this one, so I can minimize the logic equation with the help of Boolean theorems here. So this is your A bar B bar Ci, this is your A bar B Ci bar. So you may take common, that is your A bar here, that is your B bar Ci plus B Ci bar. Plus here you make, that is your what? A whole into B bar Ci bar plus B Ci. So this is nothing but your what? A bar whole into B bar C plus BC bar. It is nothing but B XOR C. That is your what? B XOR Ci plus here A whole into B bar C by I bar plus B Ci bar is nothing but B XNOR Ci. That is your B XNOR Ci. So if I'll say this is your X, this is nothing but X bar, because complement of XOR is nothing but XNOR. If this is X, this is your X bar. So I can write here, that is your A bar X plus A X bar, where X is nothing but B XOR Ci. So A bar X plus A X bar is nothing but A XOR X, where A XOR X value is nothing but B XOR Ci. That is your A XOR B XOR Ci. So one of the important conclusion is what? In case of full adder, the sum is nothing but this XOR this XOR this. So that's why A is equal to, that is your A XOR B XOR Ci. So in case of full adder, that is your, if the two significant bit along with the previous carry, the sum is nothing but A XOR B XOR Ci. So then next one is your what? That is your for carry. In case of carry, first of all we have to minimize the output for carry. For output of carry, the value of C is how much? C, that is your sigma. The mean terms are where? Where is your mean terms here? When the output is high, in this case high, in this case high, high and high. And respective input is what? That is 0, 1, 1. 0, 1, 1 is your decimal 3. Similarly here, that is your 1, 0, 1, that is your 5. Already I told you how to find the decimal equivalent of corresponding binary numbers. So that is your 5, and here 1, 1, 0, that is your 6, and 1, 1, 1, that is your 7. So carry C equal to 3, 5, 6, 7. With the help of Boolean theorems, we can also minimize this logic expression or Boolean equation. For 3, corresponding this value, corresponding input is what? A bar B Ci. That is your A bar B Ci. Plus, again this one 5, that is your what? A B bar Ci. A B bar Ci. Plus, this one is nothing but what? A B Ci bar. Plus, this one is nothing but A B Ci. Then what happened? We have to minimize it. So then tell me what, if you will take in these two min terms, where is common here? That is your Ci is common. So if I will take Ci as a common, that is your A bar B plus AB bar. If Ci taking common, plus AB is common in both min terms, so AB is taking common, that is your what? That is your Ci bar plus Ci. Using Boolean theorem, Ci bar plus Ci, that is 1. X plus X bar is 1. A plus A bar is 1. First plus first complement, that is 1. So this value is 1. This value is 1. So that's why the expression reduces to carry value. So C equal to the expression of the carry, that is A bar B plus A B bar is nothing but A XOR B, that is your A XOR B whole into CI plus AB. One of the important conclusion or one of the important derivation of the carry in case of full adder. So carry equal to C equal to what? This XOR this, that is your A XOR B whole into CI plus AB. So this is the expression for the carry. So it has two outputs in AB along with the previous carry. In case of full adder, there are two outputs. One is sum, another one is your carry. The expression for the sum equal to this XOR this XOR this, A XOR B XOR CI, and carry previous carry CI equal to A XOR B into CI plus AB. So this is all about your what? The expression for the full adder. So then if I will say what are the conclusions? So in case of half adder, the summary, or as far as the adder is concerned, so if there is a full adder, in case of half adder, it has two significant bits, A and B, and output is 2, that is your sum equal to this XOR this, that is your A XOR B, and carry is nothing but is your what? Product of these two, that is your AB, in case of half adder. In case of full adder, there are three inputs, that is your what? Full adder, there are three inputs. One is your AB, two significant bits, and considering the previous carry CI, there are two outputs. One is your sum, S equal to A XOR B XOR CI. So already I have derived the sum value, the expression of the sum equal to this XOR this XOR this, A XOR B XOR CI, and carry expression equal to A XOR B whole into CI plus AB. You have to remember when you are going to design the full adder, so that is your, the two expression you have to remember, that is your one is what? That is your A XOR B XOR CI, and carry is nothing but A XOR B whole into CI plus AB. A XOR B into CI, A XOR B XOR CI, and the expression for the carry equal to A XOR B whole into CI plus AB. Okay. So as far as the design is concerned, if I will ask you, we have only half adder, so how to get full adder? Design of full adder using half adder. Design of full adder, if I will say design of full adder using half adder. Okay, we have only half adder, we don't have full adders. So how to design full adder using half adder? So already I told you, in case of half adder, first of all half adder, the two input, that is your AB, that is your sum, S equal to what? This XOR this, A XOR B, and carry is nothing but this into this, C equal to AB. Then what happened? How to generate A XOR B XOR CI? Where is your A XOR B? Already A XOR B is there. So take one of the input as this, then another half adder. We require another half adder. We don't have any full adder. We have only half adder. So how to design the full adder? So this is your half adder, AB. The sum is nothing but this XOR this, S equal to XOR B, and carry is nothing but this into this, that is your carry equal to AB. And this XOR B taken as the input of the another half adder. Then the input is your CI. Look at this here. In case of full adder, the input is your A, B, CI. So CI as input. This half adder tell me what is your output. In half adder, if there are two inputs, the sum is what? This XOR this. Similarly, in case of half adder, the output is what? Sum. The sum value is how much? The sum value is how much? This XOR this. This value is how much? A XOR B. And this is nothing but what? Now CI. So that's why this XOR this, that is your A XOR B XOR CI. So already I told you, in case of half adder, if there are two input, one is sum, this XOR this XOR this means this value is how much? That is your A XOR B XOR CI, A XOR B XOR CI, one of the output of the full adder. And Another output is what? This into this. Remember, in case of half adder, carry is nothing but this into this, A into B. Similarly, the output must be generated what? This into this. This is value is how much? X or B. That is your AX or B into this. That is your CI. But AX or B into CI, that would be not the result of the carry of the full adder. But the result of the carry of the full adder is how much? AX or B into CI plus AB. But we have only X or B into CI here. Another AB will have to add it. So AB, this is your AB. Here is AB. AB is there. So AND gate, you will get what? This into this. So that is your what? A X or B all into CI. Sorry, this is your AB. This is your OR gate. X or B into CI. X or B into CI plus AB. Plus AB. This is your OR gate. Okay, so this output is nothing but this into this. This output is your X or B into CI, and another one requirement what? That is your AB. Where is AB? Here is AB, and this plus this X or B into CI plus AB. Plus AB. This expression is nothing but what? That is your carry. This is one of the output of the full adder. Okay, again, so how to design the full adder using half adder? In half adder, there are only two outputs, sum and carry. So sum is what? This X or this, and carry is nothing but this into this. But in case of full adder, the sum is what? This X or this X or this, X or B X or CI, and carry is nothing but X or B into CI plus AB. So there is a half adder. As far as the design of full adder using half adder, this is your half adder. If there is your input AB, the sum is what? This X or this, that is your X or B, and carry is nothing but this into this, that is your C equal AB. But we require X or B into CI. Again, another half adder. This is X or B. Another input is your CI. One of the output of this is what? This X or this. That's your X or B, X or CI. This is one output of the full adder. Then we require X or B into CI plus AB. And this is your what? This into this X or B into CI. So X or B into CI is one of the output of the half adder. And we require only what? AB. Here is AB, and there is also AB, and this is also AB. If we add these two, X or B into CI plus AB, we will get the one of the output of the carry of the full adder. So in this way, we can design the half adder, full adder using half. So thank you, students. Next class, we will also do more and more number of design of the logic circuit. Thank you.